We now know that the force is rho g AD. Rho is the mass density, g is the gravity, d is the depth, and a is the area of the slice. The area is the width times the thickness. In this formula, the depth varies depending on how far below the water level the slice is. We then set up the Riemann sum to obtain the definite integral. The force is the integral of rho g are constant, times the depth times the width, the thickness is dy. Oftentimes, in a thin vertical plate, the width of the slice depends on how far below the water level the slice is. For example, in this figure, the width is longer for the slices near the surface of the water. Thus, the width is a function of y. If we were to position y equals 0 at the water level, the depth of the slice below the water level is yi. The width is therefore a function of y. We call this L. The force on the slice is rho g dA, where d is the depth yi and a is the area of the slice, the width L of yi times the thickness delta y. Notice that L of yi times delta y is the area of the slice and depends on how far below the water level is. The widths vary. The depth is the distance from the slice to the water level. Rho and g are constant. Keep in mind that if we were to use the customary system, then rho g is delta. The total force is the sum of rho g yi, L of yi, delta y at I go from 1 to n. And at n go to infinity, this Riemann sum will give us the definite integral. Rho g are constant, so we can move rho g in front of the integral sign. If this is the US customary system, then the force is delta, the integral from a to b, y, L of y dy, where L of y is the horizontal width of the slice. Delta is the weight density.